Hi, this is a homework solution. These are the homework solutions to Chapter 8 problems. So let's start with 8.1, numbers 1, 10, 11. So number 1. So 8.1 number 1 says, suppose T is a mapping whose domain is the vector space M sub 2, 2. In each part, determine whether T is a linear transformation, and if so, find its kernel. So for 1a, T of A is equal to A squared. And so I want to check this. So T of A plus B is equal to A plus B parentheses squared, which is equal to A squared plus BA plus AB plus B squared. Okay. Matrix multiplication is not commutative, and so BA is different than AB in general. Doesn't have to be equal. T of A plus T of B is equal to A squared plus B squared. And you can see that T of A plus B was this, T of A plus T of B was this, and they're not the same. So T of A plus T of B does not equal T of A plus B. And so T is not a linear transformation because these two are not equal. Part B, T of A is equal to the trace of A, the sum of the entries on the main diagonal of A. T of A plus B is equal to the trace of A plus B. Well, if you take the trace of the sum of two matrices, it's equal to the sum of their traces. So this equals to the trace of A plus the trace of B. And that equals to T of A plus T of B. So T of A plus B does equal T of A plus T of B. Then if you take the trace, that's trace of Ka, it's equal to the, so if you take the trace of K times A, it's equal to, sorry, this is T of capital T. That's just a capital T here. It's capital T, okay? So in the file, that's a capital T. So capital T of Ka is equal to the trace of Ka, which equals K times the trace of A, which equals K times T of A. Okay, and so T is a linear transformation. Okay, and now the kernel of T is just a set of all matrices A whose trace is 0. Okay, and now for part C, T of A is equal to A plus A transpose. And so T of A plus B is equal to, sorry, this is just T of A. I'm just defining the function. In fact, you don't need this here, but just forget that. So I'll just correct that in the file, and then so that won't be there once I fix it. Okay, so T of A plus B is equal to A plus B plus A plus B transpose. That's equal to A plus B plus A transpose plus B transpose. That's equal to A plus A transpose plus B transpose. That's equal to T of A plus T of B. So T of A plus B equals T of A plus T of B. T of Ka is equal to Ka plus Ka transpose. That's equal to K times A plus K times A transpose. That equals K times A plus A transpose, which is equal to K times T of A. Okay, so T of Ka equals K times T of A. Since in both of these two equations hold, T is a linear transformation. So we can talk about the kernel. So the kernel of T is equal to set of all A such that A equals negative A transpose, right? The only way T of A is 0 is if A plus A transpose is 0. And A plus A transpose is 0 if A equals negative A transpose. So that's that problem. Number 10, so for number 10, it says let T from P2 to P3 be the linear transformation defined by T of Px equals x times P of x. Which of the following are in the kernel of T? Okay, well, T of x squared. So for A, it asks about x squared. So T of x squared equals x times x squared, which equals x cubed, and x cubed does not equal 0. So that implies that x squared is not in the kernel of T. Okay, T of x squared does not equal 0, so x squared is not in the kernel of T. T of 0 equals x times 0, which is 0. And so that implies that 0 is in the kernel of T. T of 1 plus x equals x times 1 plus x, which equals x plus x squared, and that does not equal 0. And that implies that 1 plus x is not in the kernel of T. T of negative x equals x times negative x equals negative x squared, and that does not equal 0. And so that implies negative x is not in the kernel of T. That's 10, A, B, C, D. Number 11, let T from P2 to P3 be the linear transformation in that exercise 10. Which of the following are in the range of T? R of T means range of T. So for part A, it asks whether x plus x squared is in the range of T. So I make this observation. If you take T of 1 plus x, it's equal to x times 1 plus x, which equals x plus x squared. And so there is a polynomial 1 plus x in P2 whose image under t is x plus x squared, and that implies x plus x squared is in the range of t. For part B, it asks about 1 plus x, whether or not 1 plus x is in the range of t. Well, there's no polynomial p of x in P sub 2 such that x times p of x equals 1 plus x. Therefore, 1 plus x is not in the range of t. There is no polynomial that t maps that polynomial to 1 plus x. To 1 plus x, there is none. And so 1 plus x is not in the range of t. Okay, so C is similar. There is no, so for C, it asks about 3 minus x squared, whether or not 3 minus x squared is in the range of t. There is no polynomial q of x in P sub 2, such that x times q of x equals 3 minus x squared. And so therefore, 3 minus x squared is not in the range of t. For our D, it asks whether or not negative x is in the range of t. So I make this observation: t of negative 1 is equal to x times negative 1, which equals negative x. So that means, that implies that negative x is in the range of t. There is a polynomial, namely negative 1 in P sub 2, such that t of negative 1 is equal to negative x. So negative x is in the range of t. And so that's all of 11. The next problem is 8.2 number 4. So 8.2 number 4, it says determine whether multiplication by a is 1 to 1 by computing the nullity of a and then applying theorem 8.2.1. Okay, so theorem 8.2.1 is in the book, it's on page 458 near the bottom. And so theorem 8.2.1 says if t from v to w is a linear transformation, then the following statements are equivalent or have the same truth value. A, t is 1 to 1. B, the kernel of t is equal to the set containing only 0. Those two statements are equivalent. So if you show one is true, the other is true. If you show one is false, the other is false. So for number 4a, it gives you the matrix capital A is equal to 3 by 2 matrix there. 1, 2, 2, 7, 3, 9. So I take the augmented matrix A0. So on the left side is A, on the right side is the 3 by 1, 0 matrix. I get that to reduce row echelon form using elementary row operations. And so I get this matrix right here at the right-hand side. So from this, I see that the kernel of T sub A is the 0 set, or the nullity of A is 0. Okay, so the only way in which AX equals 0 is if X is the 0 vector. Okay, because we solve for the variables here and we get that both of them are 0. So the only solution to AX equals 0 is that the solution vector X is 0. So that means the kernel of T sub A is equal to the 0 set. Equivalently, the nullity of A is the dimension of the null space. Okay, so that's 0. Okay, and so okay, so then either of these, but specifically, I guess saying that the kernel of T sub A is the 0 set implies by theorem 8.2.1 that T sub A is 1 to 1, and so that proves A. In part B, we have another matrix, capital A, which is a 3 by 4 matrix. And so I partition it with 0. So this is the A is this matrix, okay? Now I'm partitioning it here, okay? So, okay, so I'll just fix that little typo there, okay? So the A is just the 3 by 4 matrix right here. Okay, that's A. Okay, so then, okay, and so that's A partition with 0. You get that to reduce row echelon form, and you get this matrix here on the right side. And so when you look at that matrix, you see that there are 3 leading variables, but that there are 3 leading ones. But there's 1 free variable, this column. And so that means the solution space of AX equals 0 has infinitely many solutions. The kernel of T sub A is not equal to the 0 set, and the nullity of A is not equal to 0. Okay, there's dimension 1. The nullity of A is 1. The kernel of T sub A is not equal to the 0 set. And so by theorem 8.2.1, finding that the kernel is not the 0 set is equivalent to saying that T sub A is not 1 to 1. And so for part B, the conclusion is that T sub A here is not 1-to-1. Okay. And in 8.3, number 12, we have T sub A is from R2 to R3. And so, okay, so for 8.3, number 12, it says, determine whether the matrix transformation T sub A from R3 to R3 is an isomorphism. So A is the 3x3 matrix on the left-hand side of this partition. And so in order to show the goal is to show it's not an isomorphism by showing it is not one, T sub A is not 1-to-1. Okay, an isomorphism is defined to be 1-to-1 and onto. It asks whether or not T sub A is an isomorphism, whether or not it is both 1-to-1 and onto. So we're going to show that it's not 1-to-1, which implies it is not an isomorphism. To show it is not 1-to-1, we're going to just follow the same method we did for number 4 in 8.2. We're going to use theorem 8.2.1 to find that the kernel of T sub A is not the 0 set, which is equivalent by that theorem to saying that T sub A is not 1-to-1. Okay, so from the beginning, we have A partitioned with 0, and we get it to reduced echelon form. Here we see that we have 2 leading ones. We have 2 columns with leading ones in them, but 1 column that doesn't have a leading one in it. That means we have a free variable. And so the solution set to AX equals 0 is not the 0 set. The kernel of T sub A is not equal to the 0 set, or the nullity of A is not equal to 0. The dimension of the null space is not 0. It's actually 1 because of this one free variable. And so the kernel of T sub A is not equal to 0 set by theorem 8.2.1. That's equivalent to saying that T sub A is not 1-to-1. And so since we showed T sub A is not 1-to-1, that implies that T sub A is not an isomorphism. Okay, and that completes the proof of that problem also. Okay, so I'll just make these minor corrections in the sheet. Not really much there. I just need to capitalize that, cross that. And so here's the solution video. If you need more help with these problems or anything else, there's also office hour on Wednesday. Okay, see you soon.